So let's continue again. It's my great pleasure to introduce our next speaker, Professor Alfredo Chaves from Universidad Nacional Autónoma de MX, and he will talk today about cluster varieties, toric degenerations, and convexity. So please.
Thank you very much. So I would like to thank the organizers of this event and of course all the people behind IMSA for actually making a great effort to bring together these communities. So yeah, I'm going to talk about cluster varieties essentially and its relation to toric geometry. And just as Rita, I would like to highlight my co-authors. So this work is done in collaboration with subsets of these sets of authors, Lara Bosinger, who is also in Oaxaca, Manuel Cheung, Bosco Frias, and Timothy McGee. I will refer them to by BCFM. And well, most of this work was also done in Mexico. Lara and Tim were my postdocs, and here I will present some of the work we did when they were in that period. Okay, so there are some driving ideas that will be present throughout my talk, and these are these two. First of all, it's that we can generalize various constructions from toric geometry to the world of clustered varieties, and essentially this is possible thanks to a breakthrough by Gross-Siebert, Keel and Kontsevich, where they connect the theory of cluster algebras with toric geometry and mirror symmetry. And in particular, what I would like to explain is that certain projectivizations of cluster varieties can be obtained using special convex sets. Much in the same way, projected toric variety can be constructed from a polytope. So I will not assume, I don't want to assume that anyone is an expert in this field, so I will try to give some background. And in particular, I would like to talk about a notion of convexity that replaces the usual notion of convexity for toric varieties. And if time permits, I'm going to talk about toric degenerations of minimal models of cluster varieties and its connection to the theory of neutral concave bodies. Okay, so let's just talk briefly about the polytope construction of a projected toric variety. So in toric geometry, and so this is the main setting of toric geometry. I start with an algebraic torus of dimension B. So this is just a variety that is isomorphic to C star to the B. So I'm going to talk in the language of varieties. One should talk in general about schemes and so on and so forth, but to keep it simple, I will just work with varieties. And in this setting, a toric variety is just a variety X, an algebraic variety that contains a torus, Zariski opens of variety in such a way that the natural action of P on itself extends to algebraic action of the variety X. Okay. And a very famous theorem is that a full dimensional convex lattice polytope inside a d-dimensional vector space determines a d-dimensional projective toric variety. So here, lattice polytope means that the vertices of this polytope are actually integral, right? And well, let's explain this theorem in an example. So let's take D to D2. I'm working in dimension 2. And let's consider this polytope, which looks like a two-simplex. You can think that it's the simplex with vertices, the origin, and the two basic standard basic vectors. And in order to construct a variety out of this triangle, what we do is to create a graded ring. Right? So in algebraic geometry, projected variety is essentially the same that are graded ring, and we're going to use this polytope to construct a graded ring. So how do we do this? The main idea is to start dilating this polytope. Okay, so I can consider the first dilation of the polytope, which is of the polytope, the second dilation of the polytope, third dimension of the polytope, so on and so forth. And I can organize all these copies of the polytope, all these dilations in R3, right? Just like in the picture. I put the first polytope in dimension in level 1, the second polytope in level 2, in the third dilation in level 3, and so on and so forth, right? So next, what I'm going to do is to think about the lattice points of R2-3 as Laurent monomials, right? So for example, the first polytope, the first dilation of the polytope encloses 3 lattice vectors, which are if you want, the standard basis, and this corresponds to the degree 1 monomials, right? The second dilation encloses the degree 2 monomials, and so on and so forth, right? So I can just consider Ri to be the vector space whose bases are the monomials parameterized by the I dilation of my polytope, and then add up these vector spaces. If you think about it, what you obtain is a graded ring, because you can just multiply 2 monomials and you get another monomial, right? So it lies in a different graded piece. And well, these are what you obtain. It's the polynomials in 3 variables, and this is just the homogeneous coordinate ring of the projective space. Okay. So, well, this should be a toric variety, so there should be a torus sitting inside the projective space, and the action of this torus should extend to an algebraic action of the projective space. Well, this is the torus. It's just the sub-variety formed by all those points in projective space whose homogeneous coordinates are different from 0. Right? You think about it, that's a 2-dimensional torus, and this is how it works in general. So for linear use, let me just point out something interesting too. The torus has a canonical volume form, the x wedge y over xy. This is a 2 form, so it's since I'm working with a 2-dimensional variety, this is a volume form, and as you can see, this form is holomorphic inside the torus, and it has simple poles along the points that are outside of the torus. Okay. So the general picture with minus simplification is as follows. How would you just do the same? I will consider a d-dimensional polytope in a d-dimensional vector space, which is rational, so the vertices are interval points, and I will just start dilating this polytope, put the copies in the next degrees, and just collect a bunch of Laurent polynomials, of Laurent monomials, and construct a very different of this. Yeah. So it's a theorem that if I consider the projective variety associated to this graded ring, I get a projective variety together with an embedding. And well, since we're in algebraic geometry, this inclusion can be just be encoded by a line bundle, and all the points in the K dilation are just parameterizing the basis of this ring of sections. So I consider the K tensor power of the line bundle, and I consider the space of sections, and this vector space will have bases, the monomials in the corresponding dilation. Of course, this is a mildly simplified discussion because not every polytope will produce such a line bundle. What we need is to replace the polytope for an ample polytope. It should be large enough in order for this to make sense, but we can always replace a polytope by one of its dilation in order to be ample. And it will also be the case that the canonical form on the torus will have simple poles along the irreducible components of the devices that are outside of the torus. Okay, so this is what I will call the boundary, and yeah, So this is well the main construction of toric geometry that I want to generalize. So let me talk now about cluster varieties. And the idea I want to convey is that cluster varieties are just a generalization of toric varieties, where we're replacing a single algebraic torus by a copy of potentially infinitely many torus. Okay, and we're going to compactify this using complex sets. Okay, so this is quite a technical topic. So let me just first present in one example what I want to talk about. So this is going to be the running example. It's always a countable collection of toric. It's always a countable collection of toric. In many cases, it's an infinite number of toric. Okay. So this is going to be the main example of this talk, the Grassmannian of two planes in a 5-dimensional vector space. So by definition, this is just the set of 2-dimensional vector spaces inside C-path. It is a well-known fact that this is a projective variety. In this case, it's a 6-dimensional variety. And there's also, so projective varieties sit inside some projective space. And there's a distinguished embedding called the Kruger embedding that associated to any Grassmannian. Okay? So in this case, this can be very explicit. The ambient vector projective space will be 9-dimensional. So I will have 10 coordinates. And these coordinates are going to be represented by symbols Pij, where Ij are numbers between 1 and 5, and I is bigger than j. And well, the graded ring associated to this projected variety, it's the polynomial ring in the Kruger coordinates modulo some Kruger relations. So just for completeness, I'm showing what are the Kruger relations in this example, but they are not going to be actually necessary. It's like, yeah, they are not too complicated. I just want to point out that there are homogeneous polynomials of degree 2. So this is indeed a great thing. Right? There are torus acting on the Grassmannian, but they are not top-dimensional. This is not a toric variety. But what I want to talk about today is that this graded ring can also be described by a polygon. In much the same way, the ring associated with the projective space was described by a polygon. Right? And the reason why this is the case is twofold. First, is that this Grassmannian contains a cluster variety. So there's a divisor, which in this case is the vanishing of the Kruger coordinates associated to the consecutive indices. So if I remove the locus where these coordinates are 0, I get some open subvariety of the Grassmannian, and well, this will have a certain kind of structure. This will have an atlas of algebraic torus that will be glued together in a very specific way. And well, this first point is just telling that this Grassmannian is a compactification or a projectivization of a cluster variety. And the polytope arises because this is a minimal model. The Grassmannian is a minimal model in the sense of the minimal model program. This will be a condition that will be stated in terms of volume forms and non-vanishing of and poles of those volume forms. Okay, so yeah, this is the outline of this is the goal of the first goal of this talk. So let me elaborate a little bit about cluster algebras and cluster varieties. I will provide first some historical remarks. So there are two parents in two notions that are closely related in mathematics: cluster algebras and cluster varieties. Both were introduced in the early 2000. Cluster algebras were actually introduced in 2001 by Sergei Fomin and Andrei Selevinsky, and their original motivation came from some theory made in the 90s by Lustig, developed by Lustig and Kashibara-Lustig, the basis, canonical basis for quantum groups and the total positivity of reductive groups. In a parallel way, Fock and Goncharov, Vladimir Fock and Alexander Goncharov, in 2003, they introduced cluster varieties. And they were algebraic objects trying to give an algebraic geometric approach to higher Teichmüller theorem. Right? So cluster algebras, in general, they arise as the coordinate ring of distinguished varieties arising in algebraic Lie theory. For example, they could be coordinate ring of partial flag varieties, like the Grassmannian, double Bruja cells, sugar varieties, grape varieties, so on and so forth. And the cluster varieties will actually arise as modularized spaces of certain local systems in surfaces with marked points, or the marked surface. So this would be orientable topological surfaces with marked points in the boundary and in the interior. There should be closed surfaces, okay? So this example is going to lie actually within the two classes, the running example, okay? So before going into the construction of cluster structures and cluster algebras, let me just tell you what's the intuition you should have to think about these objects. And the way I want to develop this intuition is by comparing directly with toric geometry. Okay? So first of all, as I said earlier, cluster varieties are obtained by gluing a lot of algebraic toric. And the gluing is not arbitrary. It's very precise. It fits within a very precise combinatorial framework. And cluster varieties also come in mirror pairs, right? So these are like two main ideas. So let B be a cluster variety, and B check is going to be the mirror cluster variety. So in toric geometry, what I usually have, it's a torus and a polytope in this vector space. And it's important also to talk about the integral lattice inside this vector space, right? So I didn't say it explicitly, but actually the lattice can be identified as the co-character lattice of the dual torus. And well, in the cluster side, I'm going to replace this torus by a union of tori. And the lattice and the vector space are going to be replaced by staticalization of the mirror cluster, right? I'm going to explain all of these terms in a second, but it's important to have this table as a guide. It was also very important to talk about monomials in toric geometry. These are just some global functions in a torus, and in the cluster side, these are going to be replaced by theta functions introduced by Oaxaca, Keel and Kontsevich in 2014. And straight lines are going to be replaced by something called broken lines, and convexity by broken lines. So the aim of this talk is to elaborate on the cluster side of this table. And maybe, since I'm not going to be too precise on in the definition of cluster structures, let me just mention 3 ways in which they arise in mathematics. So first of all, any torus, and the right torus is a trivial example of a cluster variety, where you have a single torus. Okay, so toric geometry is going to be the trivial example of the cluster geometry set. Also, main examples of cluster varieties arise as complements of anti-canonical divisors in Fano varieties. This is the case of the Grassmannian. The Grassmannian is a Fano variety. The divisor I was talking about is anti-canonical, and the complement is a cluster variety. So this happens very often, like the partial flat varieties, like the complete flat varieties, and so forth. And the approach that people in variational geometry take is start with a toric variety, and they start doing certain blow-ups and blow-downs to construct this up. Okay, so there are 3 points of view which are kind of legal in its own way, and that there are very diverse people that follow this construction. Okay, so let's go a little bit more deep into the details of the definition of a cluster structure, of a cluster variety. So as I mentioned before, these varieties have some atlas of algebraic torus, and this atlas is governed by some combinatorial information, which is a quiver. A quiver is just a synonym of directed one. So I just have vertices and arrows between these vertices. And for technical reasons, I assume that, well, I have no loops nor 2 cycles in these ones. Okay. And well, so to any such quiver, I have 2 spaces, the A cluster variety and the X cluster variety, and these are the pair of mirror varieties that I was talking about earlier, and I'm following the notation of Fock and Goncharov. So in the context of surfaces, One of them are going to be certain moduli spaces of SL2 local systems in the surface, and the other one going to be PSL2 local systems in the surface. Okay. And the notation I will use is, in general, I will call B either A or Q, and B check is going to be what swaps these two. And I will say that a variety has a cluster structure if it's isomorphic of dimension 2 to one of these two varieties. Okay. So this is in order to really have examples. So, okay, how's the construction of these spaces? So let me just introduce a little bit more notation that is going to be very helpful. I will let N be the lattice set to the D, and I will let T be the algebraic torus associated with this lattice. This is just the lattice tensor product with C star. I can dualize all this. I can construct the dual lattice and call it M, and construct the torus associated to M and call it T check. So this is what I refer to as dual torus. So the A cluster variety is going to have a atlas of torus of the form T. So TS is here just a copy of T, and X check TS is just going to be another copy of T. And these atlases are parameterized by a regular connected graph associated to my quiver. This is called exchange graph. And I will present explicitly this construction in the example. This torus also will have preferred coordinates that are usually referred as cluster coordinates. And the main technicality of cluster algebras is the following: is how this tori glue. Okay, so there are distinguished pairs of these tori that are glued by certain birational maps called cluster transformations. And let's say I'm looking at this side of the picture, and I want to say how two of these glue together. They are going to always to be glued by some formula of this sort. So this is a birational map from a torus associated to N to another copy of the torus associated to N. So since it's a birational map, I'm just going to describe its pullback. And well, the coordinate ring of this torus, it's just Laurent monomials. And these monomials are naturally parameterized by the dual lattice M. So the pullback of one of these characters in this side of the picture is just mapped by a twisting of the character. So this is set to the M, types a binomial to a certain power. So this binomial depends on extra information, M prime and N prime. So this is like a twisting. That's an edge. Yes. Yeah, so for edges are going to be expression, exactly, birational maps of this form, and for paths are just going to be composition of those. So what is very technical about cluster theory is to describe this M prime and N prime, say like, you have a torus for each vertex and a birational map. Yes. Yes. So let me just show this in the example. Okay. So let's just exhibit the cluster structure in the Grassmann. Okay. So we said that this Grassmannian has Brucker coordinates. Okay. And Brucker coordinates are indexed by pairs of integers ij that lie between 1 and 5. So there's a correspondence between Brucker coordinates and the arcs of a pentagon, whose vertices are labeled from 1 to 5. Yeah. So let's say an edge joining two vertices labeled by A and Y, I and Y, corresponds to the Brucker coordinate PI1. Okay. So if we produce a triangulation, also you like surfaces, you can think of this as a disk with 5 marked points in its boundary. So next we produce a triangulation of this pentagon, and I just realized that this triangulation parameterizes a subset of Brucker coordinates, right? In this case, this triangulation parameterizes P13, P14, and the consecutive Brucker coordinates. So one can check that if I look at all the points of the Grassmannians whose Fluker coordinates are different from 0 for all the Fluker coordinates are measured by this triangulation, this defines a 6-dimensional torus. Right. So I just exhibit a torus sitting in the Grassmannian using a triangulation of a pentagon. Next, I said that in order to get this graph and this cluster variety, I need a trigger. And here, what I'm going to do is replace arcs in the triangulation by vertices and replace triangles in the surface by oriented straight cycles in my graph, just like here. So since this is oriented, I can just choose that the cycles are counterclockwise or clockwise. It really doesn't matter. So this graph codifies precisely the triangulation. Okay. So then I think, okay, the pentagon has many triangulations. This is one, but I can consider some other triangulation, right? Here I just decide to flip one of the diagonals of a quadrilateral. I decide to swap the diagonal 1, 3 by the diagonal 2, 4, right? So then I have two tori, the one parameterized by the first triangulation and the one parameterized by the second triangulation. Due to the Fluker coordinates, this Fluker coordinate, the Fluker relation, these Fluker coordinates are not algebraic independent. They satisfy the Fluker relation, and in this case, you can see it here. This is the change of coordinates. The coordinate associated to this guy can be expressed as a Laurent polynomial in the coordinates of this guy. Okay, an easy exercise is that this expression here, it's actually of the form of this form. So when I translate everything to the language of characters at this point, so on and so forth, this relation that I'm putting in this edge, it's of this form. Okay, so then I can consider the 5 different triangulations of the pentagon. Each one of these triangulations is right with some torus. Each one of these edges gives me a relation among the corresponding Fluker coordinates. Yeah. So this is precisely the graph that I was talking about. In this case, the graph is a 5-cycle. The cluster variety is going to be the union of these 5 tori inside the Grassmannian. And you actually can show with non-trivial effort that what you are covering is up to dimension 2, the complement of all the divisor I was talking earlier. What it's clear is that I'm sitting inside here because every triangulation has the Fluker coordinates associated with the boundary. And the torus is the subset of let's say the torus associated to triangulation. It's the set of points whose Fluker coordinates are non-zero for all the arcs of the triangulation. Right? So it is clear that I'm sitting inside this complement of this divisor, but what is not actually so easy to see, or it's not trivial to see, is that I'm covering all of the complements of the divisor. And in general, it's up to codimension. Yeah. It will depend on the parity of the vector space, whether I cover all or I don't cover all the complements of the divisor. So since I'm skipping the actual definition of a cluster variety, if you don't know this topic, you can think that this is the definition of a cluster variety, right? This is the graph. These are the tori. This is the union of tori is the cluster variety, and the way they glue, it's very specific. It's given by cluster transformation. Okay. This works in much the same way for any surface with marked points in the boundary and in the interior. I can just consider triangulation, ideal triangulations of this surface, and consider the graph of triangulations. Right. So this is, let's say that this picture generalizes to all the surfaces, all the cluster varieties of surface type. Right. The only thing that I'm not telling you is how I glue different tori, and well, this is like very the technical part that I want to keep under the cover. Okay. Okay, so now that we have a running example and that I hope we're comfortable with it, are there any questions? Okay, doesn't seem to be the case. So let's talk about minimal models. So what Gross-Hacking and Keel realized is that every cluster variety is a local Abelian variety. What this actually means is that there will be they are endowed with a polymorphic volume form, right? And that this is actually unique up to scale, just like in the torus. And this is the case because every torus has a canonical volume form, and cluster transformations preserve the volume form. So when I include two of these, then I can extend the volume form to the domain. And well, what is trivial is that these guys have maximal boundary. What this means is that they can be compactified to a projective variety where the boundary, has like different irreducible components, and there's like a zero stratum on this guy. This is actually not important for the narrative, but it's like a technical fact that actually it's important when we tropicalize these varieties. Okay, so I will call omega the volume form that these varieties have. Okay, so every local Abelian variety will have this polymorphic volume form, and it's unique up to scale. Okay. So let's talk about models of these varieties. So this lies within the framework of the minimal model program, and what I'm presenting here is a worked out definition of what's a minimal model for a cluster variety, or for a local Abelian with maximal boundary. So it's going to be a projected variety, for example, the Grossmanian, and an inclusion of a cluster variety into this projected variety as an open subscheme or as an open subvariety. And what I'm asking is that the canonical volume form has simple calls along every reducible component of the boundary. Just like in the example of the projected space, or what happens for any projected variety. So with this definition, a projected variety is nothing, it is the same as a minimal model for the torus. So examples of these are, let's say the trivial example are just projected varieties where I only have a torus, and more interesting examples are going to be partial flag varieties where associated to simple simply connected algebraic groups G. Yeah. So this is the case of the Grossmanian, for example. The Grossmanian can be presented as a taking G to be some SLN and choosing an appropriate parabolic spool. So why it's important to refer to the local Abelian property? Why it's important to consider the volume form? Well, it's going to be important because we can then tropicalize these varieties. By definition, if I have a cluster variety D, or more generally a local Abelian with maximal boundary, we can consider the set of all divisorial valuations in the field of functions of my variety that are such that the evaluation of the volume form is negative. So what's this for real? So I allow myself, so this set corresponds to all the valuations that are of the form order of vanishing and of some divisor in a variety that has the same field of functions, right? So I allow myself to change B by something that's birational, and I just compactify it and consider divisors at infinity and consider valuations that take the form order of vanishing along these compactifications of varieties birational to V. And this is the tropicalization, the integral tropicalization. And the real tropicalization can be obtained just by completion. In much the same way, the reals can be obtained from the integers, by first constructing the rationals and then completing. Of course, this looks very technical, so I'm going to try to give a way to think of these tropical spaces. So let's consider the trivial case when I'm just working with a torus. Okay. So suppose my variety D, it's just the torus TL associated to a lattice L. So here L could be the lattice N or it's through a lattice. Right? So I'm in the trivial case. and the cluster variety is just the local integral variety is just the torus L tensor with C star. So one can show with also non-trivial effort, but this is actually easy, that any certain disorder evaluation can be described as a monomial valuation. So essentially, what I take is a dual pairing with these valuations are going to be given by doing the dual pairing between a lattice vector and a vector in the dual lattice. So in this case, I have a natural identification of this tropical space with the lattice itself. So in other words, all these divisorial evaluations are just taking dot product with a fixed integral vector. And well, L I can complete it to R by the usual process of completion. So the lemma is that actually the tropicalization of the cluster varieties as sets are exactly the same as in the torus case. So for example, the X variety, it's a union of torus of the form whose co-character lattice is M, right? So any torus in the atlas will give me a non-canonical identification of the integral tropicalization with the lattice, and the same in the other side of the mirror. The real tropicalization is just going to be obtained by doing the same way, but tensor it with R. So how does it look in the example? So in the example, my cluster variety, it could be either in either side of the mirror. It's a union of 5 torus. Okay. So this actually, this is like the graph telling me how does that look. So what is the case is that every torus here, it's they are glued to each other by birational maps. Okay. So it's so the tropicalization will also have an atlas of torus. I can tropicalize every torus in the vertices of my graph, and I can tropicalize the birational maps. And the magic here is that what used to be birational, then it turns into piecewise linear isomorphism. So if you want this tropical space, we'll have atlases of vector spaces, each of them glued by piecewise linear isomorphism, right? So this topologically, it's just R, because I have a bunch of copies of R, and they're glued to each other by isomorphism. Okay. So why I'm doing this? If this topologically is on R? Well, the point is that the gluing is by piecewise linear isomorphism. So I'm losing the linear structure. So in the toric case, I only have a single copy. So the tropical space has a natural linear structure. Here, there's not a natural notion of linearity, because each one of these copies has its own notion of linearity, but they don't match up together nicely. Right? So that's why I just think of the tropical space as endowed with an atlas that comes from the atlas of the cluster variety. Okay, so now let's talk about theta functions. So this theory was born with this conjecture. This is a conjecture by Fock and Goncharov. And they conjecture that the ring of global functions on a cluster variety has a canonical base. And this canonical basis should be parameterized by the integral tropical points of the mirror. So Gross-Siebert and Keel realized that this conjecture is false in general. And in 2014, Gross-Siebert, Keel and Kontsevich actually gave conditions, nearly optimal conditions for this conjecture to be true. And they introduced distinguished functions called theta functions using the formation theory. So what they did is, I have my cluster variety that is a union of toric. They collapse the gluing in such a way that instead of being rational isomorphisms, there are just monomial isomorphisms. So then you just degenerate this gluing into a torus. And then they deform the basis of characters to the cluster variety using very nice techniques in neural symmetry. So I'm not going to recall this construction of theta functions, but let me just say that these are obtained by deforming characters of a torus in a toric degeneration. And when I was presenting my intuition, I said that I'm going to talk about well-behaved cluster varieties. So what I meant are varieties that satisfy this conjecture. And luckily, this conjecture is actually true for most of the varieties of interest arising in algebraic theory, in Teichmüller theory, and so on and so forth. Except of the torus, the ones contour torus, I think all of them satisfy this conjecture. Okay. So, okay, since I will skip the real definition of cluster variety, let me just present theta functions on example. Okay. So, in the trivial example, the cluster variety is just a torus, and the theta functions are just the characters. So, as I said before, the tropical space of the dual torus is just identified with the co-character of the defining torus. Sí, no creo que yeah. Okay. Hello? Hello? There you go. Okay, so what I was going to explain is that the theta functions are just generalization of characters. And so in the trivial case of where I have a single torus, the theta functions are just the characters. And the Fock-Goncharov conjecture is, takes the shape of well, it's the statement that says that the coordinate ring of the torus is Laurent polynomial, and the bases are Laurent monomals. In my example, I can use these 5 toric charts, torus charts, to produce the whole coordinate ring. So the coordinate ring of the cluster variety sitting inside the Grassmannian has a basis parameterized by 5 sets. 1 set for each triangulation of the pentagon, and as you can see, well, these are just monomials on the Kluckers of the parameterized by the corresponding triangulation, where I allow the consecutive Kluckers to have exponents negative, and the ones corresponding to the interior to have only positive exponents. So in particular, a Klucker coordinate is a theta function. Okay, so the main theorem relating cluster algebras to toric geometry is this one by Gross-Siebert, Keel and Kontsevich.
Here, choose to go forward and go back.
Perfect. Aha. Okay. So in order to state the main theorem relating these two pictures, I need a definition, which is that one. And I don't want you to read it. I will explain it to you. So we're assuming that let's say you can think of just a lattice, and you can think of drawing sets in that lattice. Okay. So those lattice points parameterize functions on a cluster variety. Okay. Well, I said that the tropical spaces do not carry a natural linear structure. They are piecewise linear. But what you can do is multiply points by positive integers.
Because evaluation, you can just scale it positively, and this will still be evaluation. Okay? So then you can take a subset and then consider two integers, a and b. And then you can take the a dilation of your set P and the b dilation of that set P. Each one of these dilations encloses lattice forms, integral forms. Pick two of them, one in each couple. Okay. This corresponds to functions on the cluster variety. So since these functions they are in a ring, you can multiply these functions. And since theta functions are a basis, you can express this product as sum in the basis. Okay. So you want that the theta functions appearing in that sum are parameterized by pointing the a plus b dilation of the section. Right? So why I don't want to read the definition, I'm just telling you this, is because this definition is trying to give a graded ring. A graded ring. So if I have a positive set, automatically by definition, I have a graded ring in this polynomial space in one variable with coefficient my coordinate ring of my cluster variety. And what Gross-Siebert, Keel and Kontsevich showed is that if I take the projective variety associated to this ring, I can embed my cluster variety into that projective variety in such a way that this is open inside. And moreover, this is going to be a minimal model. Moreover, they showed that there's a degeneration of this picture into the toric picture. So I can just work in some. So let's say for any torus in my atlas, I can identify this positive set with a polytope, and then I can consider the toric variety associated to the polytope, and then there's a family whose central fiber is the toric variety associated to the polytope, the generic fiber is the projective variety associated to the positive set, and the cluster variety degenerates to the torus. Okay. So this is really the main term relating the cluster picture and the toric picture. So, okay, the results I want to talk about today are these three. With shown we gave a geometric characterization of positive sets. We showed that a set is positive if and only if its broken line convex. So I will start talking about broken lines in a second. In recent work with Bossinger, Chong, and Magui, we reverse the process. Right? So if you have a toric variety that is projected, you can ask yourself, what's the associated polytope? So that's what we're answering. We start with a minimal model of a cluster variety that satisfies some assumptions, and out of this we obtain a polytope. Right? So it's like kind of starting with a variety that you know should have a polytope and producing the polytope. And in part, and another work I would like to relate to this picture. It was done first with Bossinger, Frias Medina, and Magui, in which we give an explicit construction of this degeneration. So in general, these degenerations are just abstract, and what we did is make them actually explicit. Okay, so in order to talk about broken lines, I have to talk a little bit more about the piecewise linear structure of the tropical space. So as you remember, the cluster structures are governed by a group. So the graph, the amount of toric all depend on the period. And let me go back to this picture. So as before, I mentioned this lemma that if I choose a torus in my atlas, I can give an identification of the tropical spaces with, say, a vector space or with a lattice. So say in this example, pick one triangulation, say this one. Okay, so this has a positive orthant, and what you can do is consider the positive orthant in all the different
tropical spaces in this atlas of tropical spaces and pull them back through this piecewise linear map to a fixed one. So if you do this, you start obtaining pictures of this form. Okay, so this, you can see there are 5 chambers here, and this would be the pullbacks of the positive chambers in all the positive orbitals in the tropical spaces in my atlas, pull them back to a fixed one. Yeah. So this is like an example in which I have an infinite number. If I have 2 arrows, then I will have infinite number of tori in my atlas, and this would be the picture I obtained. And probably the most important example is this. One of the most important examples. It's associated to this three double cycle, which correspond to the one punctor torus, and it's related to the Markov numbers. So in all these cases, you get chambers. And the tropical space will have a sensitive linear structure along all these chambers. And what Gross-Hacking, Keel and Kontsevich did is to complete this piecewise linear structure to all the space. Let's say if you just pull back the positive chambers, you just get a portion of the space with certain domains of linearity. And using mirror symmetry, you can extend these domains of linearity to the rest of the picture. So in order to be precise in this part of the story, we need to talk about the scattering diagrams, also called crossing structures, and I will try to avoid these technicalities and just work intuitively. So as before, you can think like in the right, you have some like parts of this picture. So these chambers correspond to pulling back positive chambers to a fixed chamber, and you can start drawing rays, piecewise linear rays. So these rays are going to be allowed to bend, and they will be allowed to bend in a way pre-described by the corresponding cluster transformation. Right? So this cluster transformation, as I said before, is governed by a pair of vertices, and this pair of vertices will tell me how much I can bend if I'm walking in a straight way. Right? So in each chamber, there's a notion of linearity, and once I change from chamber, there's a way I can scatter, and this can be done with a certain amplitude. Okay. So now we use this broken line. So a broken line is just going to be something that looks like in the right. It's just going to be a piecewise linear array that bends in the walls and ends in the interior of some chamber. Okay. So we call a set broken line convex if given any 2 rational points of my set and a broken line joining them, the broken line segment, then the whole broken line segment is contained therein in the set. And one of the terms we show is that this definition of positivity, that is algebraically, can be translated to this definition that it's geometric. So if you want in the big picture, this is the notion of convexity, right? If you just like summarize what I'm saying, like the main story is projected toric varieties can be generalized to minimal models of cluster varieties. So convexity just corresponds to this broken line convexity. Okay, so this is what we show. So this was one of our contributions in this part of the picture. So let me see. Well, since I'm a little bit short on time, I will skip a little bit the part related to Newton-Okonkwo bodies and just go back to my example. Okay, so at the very beginning, I just promised you that I wanted to describe the homogeneous coordinate ring of the Grassmannian with a polyton. So what's a polyton? Okay, so this picture should be now be familiar to you. Here I'm thinking that I'm in R7, and well, so just can think of this R7 to be the tropicalization of one of the torus in my atlas. Okay, so here I'm considering the torus associated to this triangulation. Okay, so in this case, the zeta function parameterized by the Plucker coordinate 1, 3 corresponds to the basis vector. Let's call Fij the corresponding basis vectors of the corresponding vector space. And then the Plucker coordinate of all the tropical point associated to all the Plucker coordinates of the triangulation I start with are just the basis vectors. So it's this guy, and the whole basis vectors associated to the consecutive Plucker coordinates. But when I take, for example, this other Plucker coordinates 3, 5, the tropical point is a little bit more interesting. It's this guy, and the tropical point associated to 2, 5, it's this guy, and the tropical point associated to 2, 4 is this guy. So let's say that this point that I'm obtaining, they require some computations, and in this case, the polytope is just going to be the convex hull of the 5 basis vectors corresponding to the consecutive Plucker variables, Plucker coordinates, and these 5 vectors. So it roughly looks like this, but in dimension 7. Right? So this path point actually corresponds to the cone of these basis vectors, and the polytope is just described by a convex hull, a usual convex hull. And well, let me just finish that if we replace this Grassmannian by any other Grassmannian, what I obtain is just the broken line convex hull of the evaluation of the Plucker coordinates, as opposed to the usual convex hull. Okay, so I think I will end up here.